I know, just a second. Multivariable calculus. You like that? Very good. Welcome back. This is the Tutor Wizard. I'm Adrian. This is Jasper. She doesn't want to be held anymore, but she keeps yelling in the background. So we're going to do some multivariable calculus. Very nice kisses. Okay. All right. Please subscribe right here. You'll get and hit the notification bell. You'll get notifications for this series and many other ones. Today, what are we doing? This is the Multivariable Calculus series. We're in Chapter 1, Partial Derivatives. Specifically, we're doing 1.2.3, Limits and Continuity for functions of 3 or more variables. Last time we did, the last two videos were a video just on the definition of limits for functions of 2 variables. And then we did a video on the definition of continuity for functions of 2 variables. And now what we're going to do is do the same story quickly for functions of 3 or more variables after we get this cat to stop chewing on all the equipment. All right, functions of 3 variables, then we'll do functions of 3 variables first, and then we'll do functions of n variables. It's not going to change. We're going to get more coordinates, same but different. It's an oxymoron, I'm pretty sure. Jumbo shrimp. Functions of 3 variables. If I have, now we're going to call it W, I'll call it W from now on, because what we're going to do eventually is you'll run out of alphabet letters eventually, so you have to start indexing x1, x2, x3. But for a function of 3 variables, x, y, z, remember the graph of W is going to be 4-dimensional. It's all points x, y, z, f of x, y, z, and that's such that they satisfy this, and this is inside R4. So we can't draw this anymore. I don't know how to draw in 4 dimensions. You'll see as we go. I can barely draw in 2 and 3 dimensions. 4 is straight out. But the game doesn't change, and our algebraic definition of these things doesn't change. What does that actually say? This says the same thing as it did in the functions of 2 variables or functions of 1 variables. We say that this limit, which we're going to write as this algebraic beast, we're going to say this function's limit, f of x, y, z, as x, y, z approaches a, b, c, we're going to say is L, if and only if by definition. And now here's the terminology again. This is the universal quantifier. Upside down, A is for all. This is the existential quantifier. Backwards, E is there exists. So for every epsilon greater than 0, Greek letters, it's all Greek to me. For every epsilon greater than 0, there is a delta which depends on epsilon, in fact. Don't worry, we're not going to do this too much. Such that for any point in our domain, if that point, remember, we're going to have a 3-dimensional region, but in that 3-dimensional, you're like, that doesn't look very 3-dimensional. How do you make that 3-dimensional? You're going to put some kind of, there, now it's 3-dimensional region. But in that region now, D, say, any point in there, if it's within a radius of a smaller disk inside that one, this is what that hot mess says. Geometrically, we're saying in our 3-dimensional region D, if a point in there is sufficiently close to ABC, and a ball centered at ABC, then we can show that the absolute value of our function of 3 variables and L, our limit, is less than epsilon. You're like, you explained that and it doesn't seem to have removed any. You seem to have added or removed clarity instead of adding clarity. What is that saying again? We say and write this horrible symbol and say that f of x, y, z is limit is L if when I get points in my domain x, y, z to get arbitrarily close to ABC, my function's values get arbitrarily close to L. And that's what we're saying. Next. The second thing we need, it's completely analogous to functions of 2 variables, but we'll go through the definition specifically quickly. So now we have a function of 3 variables. We say that it's continuous at a point ABC in our domain if we have 2 things. First of all, you have to check and use that horrible definition that we just did and make sure that that limit actually exists and approaches some number L. Once you have that, if that number L is in fact f of ABC, then we say it's continuous there. So there's technically, depending on the way you want to view it, 2 conditions you have to check. You have to make sure that the limit exists and is equal to f of ABC. That's continuity. Let's do a quick example. As an example, I also forgot, but I'm just going to squeeze it in here. Just like when we did functions of two variables, we then say, or one variable, then once we have continuity, we say a function is continuous on a domain if it's continuous at every point. And then we have a theorem that says functions of three variables, if they're a rational function or a polynomial or an exponential function or a logarithm or a trigonometric function, they're or an algebraic function. I know there's a list, but they're all continuous on their domains. So once you practice finding the domain of definition of something like this, what's the domain of this? As long as x squared plus cos xy is not 0, I don't want to get into what that horrible domain looks like. But wherever this denominator is not 0 is my domain. And then in there, this is continuous. This is an exponential and the ratio of an exponential and a bunch of trigonometric and this, so it's continuous on its domain. That was a really long-winded way of saying I'm allowed to plug in the values because it's continuous everywhere. So let's put this in there. That is equal to let's say the limit as x, y, z approaches 1, 0, minus 1 of e to the x plus z over x squared plus cos of xy is equal to, I can just plug in values. This is e to the 1 minus 1 over 1 squared plus cos of 1 times 0, which is equal to e to the 0 over 1 plus cos of 1. Cos of 0 is 1, which is 1 over 1 plus 1, which is 1/2. This is the limit. So again, when they are continuous, and you have a bunch of these algebraic functions, they're continuous on their domains. Once there's no problems, just like in one dimension, you can put the values in. Let's do this version in any dimension we want. Okay, let's do this one more time. Functions of 3 or more variables. The only thing that's going to change is not our horrible definition, but we definitely can't draw them anymore. If I have a function of 3 or more variables, the graph of this is now a hypersurface in a hyperdimension, which I can't draw or picture, but the game doesn't change. The only thing we do is add more coordinates, and I'll give this definition in the long version to scare you with all of the horrible coordinates. And then quickly, the last thing we're going to do in this video is give you a little bit of a linear algebra type notation to make these look like vectors instead of having to write out all of these coordinates and stuff. We're going to call this x with a bar and a with a bar, and then x bar will approach a bar of f of x bar equals, it will get nice and shorter. The structure will look the same, but more compact notation. Before we do that, let f be a function of n variables now on some domain D. We say that the limit of that function of n variables as a point in n dimensions approaches this point a1 to an. We say as points get arbitrarily close to a1 to an, this n tuple, f of x gets arbitrarily close to L, if and only if, by definition, for every epsilon greater than 0, there exists a delta greater than 0, such that for every point into my domain, if the distance between that point and the value we're approaching, if that distance is less than delta, so we're in a hypersphere in hyperspace now, if they're within that ball in n space, then the absolute value or the distance in one dimension of our limit and our function is less than epsilon. Again, what the heck is that saying? That's saying that when the distance between points in our domain are arbitrarily close to the value the n tuple we're approaching, we can make our function get arbitrarily close to the value L in one dimension. Good. Let's get the definition of continuity, and then we'll get a little bit more compact notation after I subject you to this notation one more time. Okay, same business as before, 2 dimensions, 3 dimensions, n dimensions. If I have a function of n variables, I let a point be in my domain now. I say f is continuous at this ordered n tuple a1 to an. If and only if by definition now, there's technically the 2 conditions, but I put it into one normally where they put them in the book and they hide these 2 things. The limit has to exist and L has to be f of ABC to an. So it's continuous at a1 to an, if and only if by definition we have those 2 conditions, but that limit now has to be f of a1 to an. It can't just be an arbitrary L. What does that mean? Again, in our horrible definition of limits, we just put f of a1 to an where L was. because that limit has to exist, and that limit L has to be that guy now. So by definition, one more time, for every epsilon greater than 0, there must exist a delta greater than 0, such that for every point in my domain, if the distance between that point and my value, a1 to an, if the distance between that point in my domain is less than delta, then the absolute value of my function and the image at f of a1 to an gets arbitrarily close or less than epsilon. As this gets arbitrarily close to, as these points get arbitrarily close to this point, my function gets arbitrarily close to f of a1 to an. I know. So in this course, what we're also going to do by the end, we're going to do vector calculus. So we're going to have to do some linear algebra inside of the calculus scenario. Here's your first journey into that notation. Let's compactify this. We're going to make it look exactly like this, the form, except instead of having to write out this ellipsis all the time and dot, 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 and a1 to an, we're going to give us vector notation. Let's do that. All right, to finish off, I'm trying to convince you slowly subject you to linear algebra notation. You're like, calculus and linear algebra, and yeah, eventually at first we parse them out into subjects, but eventually we want to figure out how the universe works, and whatever we need, the tools we need, happen to be, when we do functions of more than one variable, we need calculus notation or linear algebra notation as well. We're going to let x and a be vectors now viewed in Rn. So instead of writing this ordered n tuple every time, we just write x bar, and that means that ordered n tuple in my mind. And then now, once we've done that, our definitions of functions of n variables, whether you can write x as a, b, c, that's fine too. It doesn't matter if that's what you're calling them and you're in 3 dimensions, or you can write x as x, y. That looks a little bit weird, but you'll see why we do that where we have indexing. We're going to, in this course, stick to 2 and 3 dimensions. I'll rarely do more than that. But Einstein did say we would have functions of 3 spatial coordinates and 1 time coordinate. So there's 4 already. So there are reasons why we would want to look into this. However, once we do that, our notation becomes much more compact and efficient. And so here's the definition of limit. We now say as x approaches a of f of x is L, if and only if for every epsilon greater than 0, there's a delta such that any point in my domain, if the distance between x and a is less than delta, the distance in 1 dimension of our function of several variables and our limit is less than epsilon. As these points get arbitrarily close to each other, my function's allowed to get arbitrarily close to L. The same as in 1 dimension or 2 dimensions or n dimensions. Keep going. More coordinates. And of course, continuity now becomes awfully like 1 dimension. If you want to see the 1-dimensional case, now they're all scalars. Please subscribe right here by hitting the notification bell. You'll get notifications for this series and other ones. I'm the Tutor Wizard, Adrian. See you next time.